So I guess we should start by finishing what we started on Thursday, which is we had a nice example of, I don't think it was a y squared equals 8x. Is that right? Or was it 4x? Somebody should remember. I think it was 8x. No, not on Tuesday, but last Thursday, right? We were still doing these volumes. Right. I think, was it 4x? 4x squared. Oh, was it y? No, it wasn't y squared then. I think it's 4x. I think that's what we were. Or 8x. That's what I thought. I knew it was 8x. What, the 8x? Oh, no. We weren't, not the one on the homework. No, I think we were doing one. It was at the end. We started rotating it around different lines. I think it might have been. Is it y squared equals 4x? Oh, it is. So it's just y equals 4x squared? Okay. I told you it wasn't what I said it was. Okay. And, well, of course, let's just quickly graph that up. And this, of course, isn't enough information because we don't have a region bounded. So I must have given you something else, maybe x equals -1. Is that what you mean, what I was rotating around? No, I mean, what's my region bounded by? I think it was something like x equals 2, maybe? Okay, let's go with x equals 2. Okay. And then we're also bounding by the x-axis. Okay, so that bounded below. Okay, that's y equals 0. Okay, and so we get this region here. And last time we rotated around, was it x equals 1 or y equals -2 or something? Okay, so let's do it around a different axis, right? If we already did x equals -1, let's do it around something else. How about we do y equals -2? So there's y equals -2. And we're going to take this and rotate it around there. Okay. So let's keep with this philosophy that we can only rotate around x-axis or y-axis. Okay. Let's just keep with that philosophy. So this is y equals -2. It's not the x-axis. So what do I do? How can I get this into a position where it is? Well, see, if I move it down 2, that's really bad, but presumably you mean... Right? Yeah, shift everything up 2, right? If we shift this up 2, and this will follow it, right? That will go up to the x-axis. Okay? So we just take the graph and move it up 2, move this up with it, and now when you rotate, of course, you're getting the exact same thing. Right? But now at least it follows our philosophy of, okay, always go around either the x-axis or the y-axis. Okay, so let's shift this thing. Okay, so if I shift it, well, it starts over here at 0, 0, so I better shift it up 2. So 1, 2. Of course, x equals 2 doesn't go anywhere. Don't really have to worry about shifting that thing up. Remember, we bounded by the x-axis. Well, that's got to shift up as well. All right, so that's now y equals 2. So there's our region again. So we've just moved the region. Right? And instead of rotating around y equals 2, we're going to rotate now around y equals 0, which is the x-axis. It's the same thing. We've just kind of picked up our coordinate system a little bit and shifted it. Okay, so that's a new function. Okay. if I take my function 4x squared and I move it up 2, I get a new function. And what is that new function? How do I describe this equation? I should write this. Yeah, 4x squared plus 2, right? That's how you do a vertical shift, right? You just tack a plus 2 on the end. Okay, that just moves everything up by 2. Okay. So now we compute the volume. So let's see. It's a function of x going around the x-axis. So there's just one variable, so I use the pi formula. Okay, and the pi says I have to integrate from something to something. Okay, well, what is it? Well, you're looking on the x-axis. You're integrating from 0 to 2. So we're just going from here, right, here to here. That's 0, that's 2. Just integrate along the x-axis. And then, well, it's the pi. Where does pi come from? I was going to say a pi crust and filling. And, yeah, of course, it comes from pi r squared, right? So you need to take the function squared minus the bottom function squared, right? The top function squared minus the bottom function squared. Okay. Now, it used to be that the top function was 4x squared and the bottom function was y equals 0. Now, the top function is 4x squared plus 2, and the bottom function is y equals 2. Right? So you got to incorporate that. Okay. So the top function is 4x squared plus 2, and we square it. And then we subtract the bottom function, which is 2 squared. Okay, so let's pause and make sure we agree with this. Okay. A function of x around the x-axis, so we use the one variable, 1 pi formula. That's pi r squared. Right? And when your region is bounded by an upper function minus a lower function, right, you have to square them individually and subtract. Because what you're really doing, if you didn't have this, you'd be computing this whole region down to the x-axis rotated around. And if you didn't have this, you'd be computing everything below y equals 2 to the x-axis rotated around. And so since you don't want this area, you subtract it out. Okay? That was the thinking behind this formula. Okay, so now it's just a matter of algebra. So let's see, if we square this, we're going to get 16x to the 4th plus, let's see, 2 times 2 times 4 is 16x squared. And then we get plus 4. And then we're going to minus 4. Oh, that's nice. That's nice. Okay, so that just goes away. Okay, so, well, why don't we pull this 16 out? Because no sense making a mistake with that lying around. So we'll have 16 pi outside. So then we have to integrate x to the 4th, which is just a 5th x to the 5th. And then we integrate x squared. That's a 3rd x cubed. And then we have to evaluate at 0 and 2. Well, it's nice. The 0 is not going to do anything. And the 2, oh dear. Let's see. So we have 16 pi. You plug in a 2 and you get 32 over 5. You plug in a 2, you get 8 over 3. And let's see here. That's 96 plus 40. Right? We're doing the cross multiplication trick, right? 96 plus 40 is 136 over 15. So 16 pi times 136 over 15. And, well, I'll let you combine 136 and 16 if you like. But actually, what I would do first is I would factor out an 8 from here. I know that's going to be nicer for there. So it's 2 to the 7th, that's 128 times whatever's left over. Well, there you go. Yeah, okay. So now we feel enlightened because we got that. All right, of course, all the interesting stuff went into setting up that integral, right? Everything after that is just computational. Yeah. Okay. Let's try something else just to see what happens when things get really bad. Remember these two setups that I did always had you having a region up here, right, in the first or the second quadrant. Okay? And you always had to go around an x-axis or a y-axis. We've already seen what you can do if you are told to rotate around a different axis, right? You can just shift your graph, okay? At least when it's starting up here. But what if it's really bad? What if you're starting down here, for instance? Right, what do? Well, Lace says just move it. And roughly speaking, yeah, that's all you can always do that, right? Right? If you want, and of course, when it's down here, you have to decide, oh, am I really talking about, do I care about the fact that things down here should evaluate to be negative? Right? And if the answer is no, if all you care about is the absolute value, okay, then you don't mind. You can move it anywhere you want to. Right? If it is, if you do mind, then you have to be careful. Right? So let's see, though, if well, let's take the same region again. So we have our picture over there. And, well, let's just go back and add in something. Let's say we wanted, I think before we rotated around, was it -1? And what we did is we just shifted it over, right? When it was -1, we shifted this over so that we could rotate around the y-axis. Well, let's see what would happen if we put the x on the other side. Right? Let's put the x, the axis over here. Let's say at x equals 4. Okay? And now I want to rotate that way. I mean, the first thing you think of, well, is move everything over to the left, right? That'll get this axis back to the y-axis. Yeah. Yeah, actually, in this case, it's really not a problem. So with this function, it's not going to be a problem, and the reason why is this. With the one variable case, you have more freedom. You're allowed to use both quadrants. Okay? Remember in the shell method, though, right, the two variable, then you were only allowed to use the first quadrant. That was the rule. So in this case, you're not going to have a problem. You just move it over by 4. Okay, boom, fine. You have something over here in the second quadrant. That's okay because you're using the disk method. Right? Okay, so let's try one where we are starting with something where we're going to have to use the shell method. Right? So maybe 4x squared is not a good one. Let's just turn around and make it 4y squared. So now our function is looking like this. And let's say we again put down x equals 2. And we'll go above the x-axis. So we get this bit here. And I want to rotate this around x equals 4. And I want to use the shell method. Okay, so the 2 pi formula. So let's see, so we're bounded by x equals 2 and also y equals 0. Oh, bugger. Wait a second, did I just snooker us? I think I snookered us. Why do I snooker us? Well, now we're actually, if we shifted it over, it would be in the y-axis, and we have a function of y, so we'd be in the disk method, wouldn't we? Okay, so if I want to use the shell method, I'm going around the y-axis, then I guess I'll have to write things in terms of x. No? Okay, so this thing becomes, well, since we're over in the positive stuff, we'll get a positive square root of x over 4. Okay, so we have a function of x, but we're trying to go around something which looks like the y-axis. Right? At least it's going in this y-axis direction. Okay. Okay, so again, what we would like to do is just take this graph and move it over to the left. Right? But we can't do that and rotate around the y-axis. Why not? If I take this picture and I shift it to the left by 4, so that this axis of revolution becomes the y-axis, what happens to this region? Where does it go? It goes into the second quadrant. But we're using the shell method. You're like, what? Oh, second coordinate. Second quadrant, yes. Okay. Yeah, it goes to the second quadrant. But the shell method says we have to be in the first quadrant. Right? So that's a problem. So what can I do? Now I've got to use the shell method here, right? Okay, so of course you'd say just use the disk method. Why not use the disk method? Fine. Right, just for instructional purposes, right? We're going to use the shell method. What do you mean shift it? Now the y-axis is fixed here, but here's what I want you to remember. Volume is invariant under translation, right? You can move it. It's also invariant under rotation. Okay? If I take a tennis ball and move it up and down, the volume doesn't change. If I rotate it, still the volume doesn't change. Okay? So if I move this piece around and then rotate in the same way, right? It won't hurt anything. I can also rotate this thing. Right? I could reflect it, for instance. Right? Yeah, what if I put a negative here? I turn this bit around. Right? And then I have to move the x equals 4 over, too. Right? Everything just gets flipped. Basically, I hold up a mirror to this thing. Okay? So what happens if I do this into a mirror? Well, if I do this in the mirror, whoops. Okay, the x equals 2 becomes x equals minus 2, right? There's your y-axis. Okay, and what you were supposed to be rotating around x equals 4 becomes x equals minus 4. Okay, and of course, this thing doesn't do anything when you rotate it, and so now rotating this way. And now, right, you push everything back. Okay, now you take this minus 4, push it over, right, back to 0, and then this bit pushes over. Right? And now you can rotate around the y-axis, and you have something which is in the first quadrant. Does that make sense? Dina says no. Okay. What's the difference between... okay, so in this case, let's say we just start off and say, okay, let's move this over to the left. Okay. Then our region is now over in the second quadrant. Okay. But our shell method only is designed to work when your region is in the first quadrant. It has to be over here in the upper right. Right? So if you just move it over, you can't use the shell method, which we want to use. Whereas here, first rotated it around, and now all your pushing is going to the right. And when you push it to the right, now this stuff goes back into the first quadrant. Right? So we're going to take all this stuff and shift it over by 4. Right? That's going to get shifted over by 4. Okay, so let's draw the next picture, right, which combines it all. Okay, so we started off with this thing with a vertex at 0. Right? We rotated it, and the vertex is still at 0. Okay? Now we want to push it 4 units to the right. So the vertex will be at 4. So 1, 2, 3, 4. Okay. Now we have all these other guides that went with us. We started off at x equals 2. When we rotated it across, that became x equals minus 2. And if we push it 4 to the right, where will minus 2 go? Go to positive 2. So you get this nice region up here. Of course, again, when you push everything to the right, the x-axis doesn't go anywhere. It just gets stuck. Okay, now we had our axis of revolution. That was x equals 4. We rotate across, and it became x equals minus 4. And now we push it 4 over, and it becomes the y-axis. There's your y-axis. And notice, the volume you're going to get out of this is exactly the same volume. Okay, all we've done is rotate this thing or translate it. Okay, we've just moved a tennis ball. We either spun it or we moved it. Okay, the volume is not going to change. Okay, now the problem is we need to figure out what happened to the function, because it's not the same function anymore. You've changed. Okay, so let's start. Since we're doing things horizontally, let's see. Well, I guess we can start from here. When you reflect a graph horizontally, how does that show up in the function? It's not that it's an even function. We're really doing something to the function. So, okay, which one is it? Is it negative f of x or f of negative x? So what would negative f of x do? Well, f of x is your output. That's your y value. Okay? If you put a negative in front of it, it negates your y value. So it takes a y value up here and negates it. Moves it down. So what is it doing to the graph? It's a vertical reflection. Right? What about this one? Well, this says whatever your x value is, take the negative of it and let that be your new y value after you apply the function, right? So it's just swapping the role of x and negative x. So It's related to even. I mean, the definition of even function, all right, says that this, right? That's the definition of even function. Okay, but of course we don't have that, right? We have a function which is far away from being even as possible. It's not even defined on the other side, you know. Well, at least in terms of x, right? You can't put in negative numbers in here. But in any case, okay, what we're doing here, let's not confuse the issue, right? To do a horizontal reflection, right, you have to negate the x values inside. That'll do a vertical reflection. That'll do a horizontal reflection. Okay. So here, we got a new function. Y equals the square root of negative x over 4. Now you might be thinking, whoa, 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 whoa. You can't stick negatives under the radical. Why is that okay here? It's okay. No, it's a function. Well, as a function of x, remember, we're only looking here at the upper half of this parabola because we don't care about anything down below. Right? Because this region is bounded by the upper half. Right? Typically, I would have to put plus or minus here when I solved for y. But since I'm only dealing with the upper half of this region, I can use the positive one. If I was looking at this region down here, I'd have to use the negative one. Okay? So that's not a problem. It's really a question of domain. What are the x's that are going into this? They're all negative numbers. So if I put a minus in there, boom, makes them all positive. Which is exactly what you wanted, right? Is you want this to mimic what would happen if you'd have done it for positive x's. Okay? That's why we put in a minus x. Okay, so that gave us this. Now how do we move it over by 4? Yeah, so if you're moving to the right, then you should subtract 4. Okay, so let's see if that's right. Now, do I do it like this? No, what would that do? That would move it down by 4, right? That would be a vertical shift. Okay, so where do I have to put the minus? Put it on the inside. Okay, is this right? So you think the shift should come before the reflection. Okay, well, let's check. Right? How do we check? Well, we plug in some numbers. Okay, we just check to make sure. Okay, that should be 4, right? Because we wanted to be going around. Oh, wait a second. Well, yeah, that's okay. That's just is what it is. Right? It's 4 because we took the vertex, which was at 0, and we moved it over 4 units to be there. Okay, now if I put in a 4 here, I would get minus 4. Minus 4 is minus 8. Ooh, that's bad. Right? Okay, so seems we're right. You have to do the shift first and the reflection second. Okay, so you do the shift and then the reflection. Now let's see. If you plug in the 4, you get 4 minus 4 is 0. Minus 0 is 0. Divided by 4 is 0. Square root of 0 is 0. Boom, it's right where you want it to be. Okay. Good. And of course, if you look up the notes from last term that I had at one point on the web about all this stuff, right, I had these acronyms that I also asked you to find names for, and nobody did. So this meant horizontal shift first, reflection second. But with verticals, it switches. Vertical reflection first, shift second. And I have mnemonics for these, but they're not appropriate for classroom use, it seems. I think in those notes that I put up there, I gave some other ones that are not nearly as interesting. Yeah, you can ask any of my pre-calculus students from Santa Cruz how they remember this. I guarantee they all remember it. Okay. What's that? It may be outside of class, yes. It would definitely off camera. We can talk about these things, and I don't want to offend anybody, either in the room or our listening audience in Zimbabwe. So we have somebody in Zimbabwe who watches these. It's according to Google, anyway. Yeah. Hello, Zimbabwe. Okay. All right, so now we have a function, right? It's a function of x, and we want to, well, let's see, go around the y-axis. So that's a function of x around the y-axis. So that's two variables, so we have to use the 2 pi's, right? Because we're using the shell method. So let's just set it up over here. So the volume should equal, all right, like I said, we're in the 2 pi case. So we're going from now 2 to 4. Right? You always use as your limits of integration the variable that matches the variable of your function. Okay? Since this is a function of x, we're using the coordinates on the x-axis. Okay? 2 to 4. Okay? And now we need the top function minus the bottom function. Well, the bottom function is just 0. So it's just going to be the top function. Okay? We're going to need that in there. But we first remember, this is the 2 pi. 2 pi came from 2 pi r, so we do 2 pi x. So I put in an x, and then I put in this function. Okay? So my function is minus x minus 4 over 2 dx. Oops. Parentheses. Thank you. Oh. I'm sorry, what were you saying? Pardon? Well, okay, if you put a 4 and then you square root it, it becomes a 2. So, I'm just being funny. Are you mocking my humor? He's quick, Okay. This is not that complicated to do, but you have to see how to do it. Yeah. Shirley, what would you do? You don't know? Well, let's turn this back into the 2. And let me pull the 2 out. Okay, it does look a little bit nicer, I think. Yeah, you could. You could make this minus x plus 4. Does it help you any? Not really. Okay. Just to get things moving. Yeah. So what would you try on this? Substitution. Great. What's your substitution? Okay, let's try that. Now, that'll be really nice here, right? You'll get a u to the 1/2 power, right? Square root of u. You'll have to toss a minus out there, and then that'll turn into a du. But then you still got this x lying around. Okay, exactly right. We can solve this equation for x. Okay? And you'll get x equals 4 minus u. so that we then get, okay, we have to pull that minus sign out so that we can swap our du's. Okay, now I want to be careful here. I'm going to write x equals 2 and x equals 4 because these were really the x's, not the u's. And then x became 4 minus u, and square root of minus x plus 4 became just square root of u, or u to the 1/2. And now this is not so bad, right? I can multiply this out. Okay. Let me see. Let's fix these deals here. So when x is 2, you get minus 2 plus 4, which is minus 2 plus 4. That's 4 minus 2. 4, 3, 2. 2. Good. Okay. And when x is 4, you get minus 4 plus 4 is 0. Right? Is that okay? Yeah? Right? When I put an x equals 4 into here, I get minus 4 plus 4. So u will be 0. I know it looks a little weird, huh? But remember right at the beginning when we defined the definite integral, we said this was going to be okay. We just gave it a definition. It was just going to be the negative of what would happen if it was from 0 to 2. Okay. We'll see if we get everything right. If we get a minus sign off, then we'll know we just have the minus sign problem. Okay, and then this stuff, well, let me just multiply it out. 4u to the 1/2 minus u to the 3/2. Okay. So let's see here. 4u to the 1/2. So you got to add 1. That gives you 3/2. Then you have to divide. So it's 2/3 times 4 is 8/3. U to the 3/2 minus. Okay, you got to add 1. You get 5/2. You got to flip that. You get 2/5. U to the 5/2. And then we have to evaluate at 2 and 0. And when you evaluate at 0, of course, everything goes away. Isn't 0 nice? And then you have to subtract what happens when you evaluate at 2. So that'll cancel with that negative, I guess. So we'll just plug in 2 here. So, okay, now let's see. 2 to the 3/2. That means you do 2 cubed, which is 8, and then you take the square root. So square root of 8. So 8 root 8 over 3 minus, now you have to do 2 to the 5th, which is 32. And then you do the square root of 32. So 2 root 32 over 5. Now we better make sure this is a positive number. So we can simplify a little bit here. Pi. Okay, so root 8, that's the same as 2 root 2. So the 2 will get sucked in here, and I'll get 16 root 2 over 3 minus, now root 32 is not 8 times 2. Yeah, it's 16 times 2 right under the root, so 4 root 2. So 4 times 2 is 8. So now we get 8 root 2 over 5. Right? Okay, and now it's pretty clear, right? This number is, I mean, it's bigger on the top and it's smaller on the bottom, so this is definitely a bigger number. So this is positive. Okay, and we could add these if we wanted, but okay, at least now we're happy. It's a positive number. Okay? This is much bigger than that. Okay. Now, why, by the way, did it happen? Ooh, I gotta stop here. Why did it happen that our limits of integration got all jacked up? Why are they going the wrong way? Right? I mean, they're going from 2 to 0. That's not how we normally want them to go. I mean, it doesn't matter, right? You could just swap and add a minus sign. All right, but why are they going the wrong way? Yeah, well, I'll tell you, it's because right here, when we did the substitution, u equals minus x plus 4, right? The u is going the wrong direction, right? As x goes up, u goes down. As x goes down, u goes up. Right? So as x goes from 2 to 4, u's got to be going down from 0, well, from 2 to 0. Well, I mean, what you can do, the alternative, keep it from 2 to 4, but when you get to the end, right, when you evaluate the antiderivative, turn it back into x's. Right? If you don't turn it back into x's, then you're getting the wrong answer out in the end. Right? Because, I mean, you can imagine, if you plugged in 2 and 4 instead of 2 and 0, you'd get a very different number. Right? And the problem is, when you make the substitution into u's, these limits have to be changed too, right? Or at the end you can substitute back your x's. Then you can keep the 2 and the 4. But you have to make a choice. Either I switch everything to u's, and then I don't have to substitute in the end, right? At the end I don't have to resubstitute. Or I leave my limits, but I have to put my x's back in at the end. Your choice. You can do it either way. You get the same answer. Okay. Okay. So the lasting moral here is you can always do these rotations and reflections to move these things, your region around the board, all right, so that you can end up with it being in the first quadrant if you need it to be, if you're using the shell method. Okay. You just do it systematically and remember these rules.